Good day. These are the notes for acids and bases, worksheet number 1. Acids that you might eat have a sour taste. For example, oranges, buttermilk, lemons, Sour Patch Kids. Bases tend to be bitter in taste and slippery to the touch. Example might be soap. I haven't personally tasted ammonia, but that might taste bitter. Baking soda is also basic, and it does have a funky, bitter taste to it. What is a proton in this chapter? A proton in this chapter refers to H+. Meaning it has only one proton. That's why it's called H+. It has one proton, H+. A proton is considered to be acidic. Bases are mostly composed of OH-, that's called hydroxide, but there are other substances that create a basic solution. Examples, ammonia, which is NH3, or ammonium, which is NH4+. Arrhenius acids and bases. Svante Arrhenius. He was a Swedish scientist who taught himself to read at the age of 3. In general, H+ ions are acidic and OH ions are basic on a pH scale. That's what Arrhenius said. And he said acids produce H+ ions. For example, nitric acid, when it's put into water, breaks up into the H+, which is the acidic part, plus NO3-. And then he said, which is according to Arrhenius, that bases produce OH ions. So if you take sodium hydroxide and dissolve it in water, you get Na+, which is not basic, but you do get the OH- part, the hydroxide part, which is basic. I like to say Arrhenius was erroneous. Arrhenius acids and bases are restricted to aqueous solutions. This means that solids cannot be acidic or basic, although they are. The sugar coating on Sour Patch Kids is a solid, and it is acidic. The Arrhenius definition only allows for one type of base, an OH hydroxide type base. This is not true. There are other substances that are basic. Bronsted-Lowry acids and bases. Johannes Bronsted, he was a Danish chemist, and Martin Lowry, he was an English chemist. They said that acids are proton donors, meaning they give away H+. For example, HCl is acidic because it gives off or gives away the H+, and then you have the Cl- part, which is not acidic or doesn't affect the acidity. And the big difference they have from the Arrhenius acids and bases is that they say bases are proton acceptors, so they accept H+. So in H3, which is ammonia, if you have it floating near an acid H+, it could take that H+ and become NH4 positive. So according to Bronsted-Lowry, bases are not just OH- donors. They're actually proton acceptors. This definition has broader implications than the Arrhenius definition. Where does the proton come from? What really happens when an acid is dissolved in water is this. You take the acid, you put it in water, and you get an H breaking off from the HCl, and it actually goes to the water part, and you get 3 H's and 1 O, and if you add one more H, you get a positive charge. And there's Cl all by itself with a minus charge. And what's interesting is that the negative part on the Cl is canceled out by the positive part on the hydronium ion, H3O+, and so each side is technically neutral. H3O+ is called a hydronium ion, and generally it's shortened to H+, because that's the part we're concerned about. That's the acid part. Conjugate acids and bases. Acids start with the letter H. Bases in general have OH in them, and conjugate acids and conjugate bases come in pair. You can't have one without the other. So every acid has a conjugate base, and every base has a conjugate acid. A conjugate acid is what results when a base adds one H+, and a conjugate base is what results when an acid gives up one H+. And so when an acid gives up an H+ to become a conjugate base, the conjugate becomes one more negative. What does that mean? So the acid HCl, it loses an H, and what you call the Cl- leftover part is actually the conjugate base. So hydrochloric acid is the acid, and it has a conjugate base, which is Cl-. But when a base accepts a hydrogen plus, it becomes one more positive. For example, the base NH3, if it accepts an H floating from somewhere in the pot, you would get NH4 plus because you took on a positive, one more proton, and you don't have any extra electrons to balance that out to 0, so it's an NH4 plus. Conjugate acid and base pair practice CACB. Find the conjugate base of the following compounds. So every acid has a conjugate base, and it is going to mostly be the anion. So HCl is Cl minus, HBr, the conjugate base is going to be Br minus. I'm writing with the mouse, so it's not perfect. HNO3 has a conjugate base of NO3 minus. HCN, hydrocyanic acid, has a conjugate base of Cn minus. And this one's a little bit trickery-dickery doc. This one has a conjugate base of SO4. And this one's trickery than that. It actually still has one H on there. It lost only one H. So it still has one H left over, and the charge on that is 1 minus. That one's trickery-dickery doc. Find the conjugate acid of the following compounds. So the conjugate acid is when you add an H. So H2O, you add an H, it's going to be H3O with a plus. Where's my plus? And ClO3 minus is going to add an H, and it becomes one more positive, HClO, and it's going to be, gotta have that 3 there, it's going to be neutral. If we add an H to this one, it's going to be H2PO4, speaking really slow because I'm writing slow, H2PO4 with a 1 minus, that's a bad 1 minus. And then if you have a conjugate acid of ammonia, you add 1 H, which becomes NH4, and then with a 1 positive. Shazam! Boom! More conjugate acid and conjugate base pair practice. Identify the acid base, the conjugate acid, the conjugate base in the following. You know this is going to be on a test. So the acid is the one that gives up the H. So this one is connected to that one. This one must be the acid because from the left side to the right side it lost an H. And then we look at this one's a pair, and that one gained an H, so that makes this the base. Acids and bases are always on the left side, and the conjugates are on the right side. So a base always has a conjugate acid. A base doesn't have a conjugate base. And an acid always has a conjugate base. They're opposites. And the reason being is that if you went backwards, meaning the reverse direction, now this H3O thing could act like an acid and give up the H, and the Cl species could act like a base and gain a hydrogen. And that's where the conjugates come in. One more. So NH3 and H2O. So I match up the pairs. NH3 must be paired with NH4, and the H2O, don't laugh too much, I like to write water like this, H-O-H, the whole rainforest. And that one is connected to that one. So now we ask ourselves, which one is the acid? The acid is on the left side, and it's the one that gives up an H. Did this one lose an H? No. Did the water lose an H? Yes, it did. The water is the acid. How crazy is that? And that means a base should have gained an H, and look at that, it did. That one gained an H. So let's check out the acid and double check. So every acid has a conjugate base. Shazam, it did. Look at it, lost an H. And every base has a conjugate acid. It gained an H. That is the Ca. So it goes B-A-C-A-C-B. Aha, your homework is worksheet number 1, and it's 1 through 9. It's the whole thing. Have fun!